to a tired grad student, and so, you know, but still, it's very impressive. These numbers are like 95% for the top 5 accuracy. Of course, there are other applications. One is just scene parsing. So semantically segmenting an image and then labeling what the different parts are. There's also been great progress in deep learning for audio, so speech recognition and video, so action recognition. So it's really pretty cool. Okay, so I'm gonna give a quick demo to break up my talking here. Let's see if all this shenanigan with the computer left my demo. Okay. So, aha. Can you guys see that? Is that good in size? Excellent. So here I'll be using the GraphLab Create product, which is the product Dato makes, but just to demonstrate how you would train a deep learning model. Okay. So first I import GraphLab, and then I import my training set and my testing set. And the task at hand is going to be detecting cars. I'm going to clear the output so I don't spoil everything for you guys. So basically I have some set of images that have cars, some set of images that doesn't have cars. And we're going to try to detect which ones are which. So I loaded the data into what we call an S-frame. Then I'm showing the images in the S-frame on the left. So you can see they're small images, but the middle two have cars, and the top one is not a car, and the bottom one is an example of not a car. There are in total, I believe, about 1,000 images. Okay, so this is where we actually go ahead and train the model. I call GraphLab.NeuralNet classifier.create. I put in a data set, which I call train. Target is basically just the label of each image that we're training for, and I don't want there to be a validation set in this case. And that's, okay. This is the network that GraphLab Create chooses. As you can see, it has initially a convolution layer, it's followed by a max pooling layer, and then it walks right into a full connection layer. So this is very similar to what we were discussing before. And so I ran 10 iterations, and it processed about 6,000 examples a second. And so even though the images are small, it's still quite fast. This is running on GPU in AWS right now. So one danger of having quite complex models is that they might overfit. So let's evaluate on our predefined test set. And we see that we actually do get remarkably good accuracy. We get 98% accuracy on determining whether there's a car or not a car. And we do it all quite quickly and easily using GraphLab Create. Now, these numbers are great, but it's nice to be able to actually visualize what we're looking at. So I'm going to look at the inputs that are least likely to be a car. So let's look at these. So the score represents the probability that it's in some class. The class is negative, so that means that there's no car there, or that it thinks that there's no car there. Okay. And in fact, in these images, there's some river, there's, I think, a washing machine, some buildings, a helicopter, and no car. It's pretty cool. Let's do the same thing for most likely to be a car. And they're all cars. They're all the side of the car. Now, there are, if you go back up, you'll see that there were a few misclassifications. There were 4 misclassifications out of the full test set. And so let's take a look at 2 of them. Basically, we're looking at things right now that the algorithm thought were a car, but weren't really a car. on the right, you see a motorcycle. I feel like, for me, that's a forgivable result. It also has a wheel. It's also a mode of transportation. And on the left, this image is very blurry, but I claim that there's a car in the background. So, you know, good mistakes. Maybe they were, it was mislabeled on the left there. Cool. So as you can see, for small problems with small networks where you don't have a lot of data, but you also are not training, you don't have to discriminate very challenging things, so you can have fewer parameters, it's quite easy to use GraphLab Create. Let's go back to the actual thing. Okay. Nevertheless, there are still some challenges of deep learning. First, the pros though. We have learned that we can now learn features rather than hand-tuning features and creating features. We have seen that we get impressive performance gains in things like computer vision or speech recognition and maybe some text. And of course, there is a potential for much more impact. Nevertheless, there is no such thing as free lunch. So in order to understand some of the cons of deep learning, let's take a look at what the deep learning workflow actually looks like for problems on any kind of scale that are bigger than this car problem that I just showed you. So first, you need to collect lots of label data. This in and of itself can be expensive. Maybe you don't have access to data streams. Maybe you don't have access to labels on that data. So you might have to mechanical turk it, outsource the labeling. It can get very expensive and very problematic. But assuming that you have lots of label data, then you split things into a training set and a validation set. No surprises there. You learn some deep neural net model, still no surprises. And you validate it, and you're probably not very happy. These models are very finicky. You have to get just the right architecture. You have to get just the right hyperparameters. So I mentioned before that the model is trained with stochastic gradient descent. You have to get the right learning rate. You have to get the right weight decay. It's basically an infinite number of combinations, and each training of a large model on a large data set takes a lot of time. So it's extremely hard to tune. And so, you know, this might not be a problem for the Googles and the Baidus and the Yahoos of the world, where they have lots of resources, lots of smart people, and also just like incredible hardware. They can just spin up a ton of these things and just let them fly and then choose the best one. Nevertheless, if one of us at home wants to use a deep learning model, we're kind of hosed. So the question is, can we do better? Can we get over those cons? And the answer is, of course, yes. But let's stop and think about a key observation here. So when you train a model, let's say for recognizing faces, and let's just say for the sake of argument that we're discriminating between Bob and Jane, and somebody has already done this for you, you have a model which can already discriminate edges. In fact, can also already discriminate things like noses and eyes and eyebrows and such. So wouldn't it make sense that the same features are useful for discriminating between myself and Rajat as well? I mean, we also have noses and eyebrows. And so that's an idea that has been explored with much success. Okay, and this is where this idea of deep features comes in. Basically, you take deep learning, you take the idea of what I just talked about, transfer learning, and you become a winner. So just to go through the transfer learning workflow, you have on some task lots of data. You can learn a neural net. Maybe somebody has already done it for you. Maybe there's been a paper published about it with results you can recreate, and you get great accuracy there. Now you have a related task. Doesn't have to be, it turns out, even very related, but a somewhat related task, let's say in the vision domain. You use the previously trained neural net as a feature extractor, and now for each image, you have some representation, and you can train a simple classifier on top of it. And now you have great accuracy on your new problem, and you expended hardly any energy doing so. So let's just go into a little bit more detail about this. This is back to our AlexNet model. So remember how we have sort of more general features learned at the beginning and very specific features learned at the end. So what you can do is for task 2, you can just throw away the last layer, or maybe the last 2 layers, maybe the last 3 layers. How far back you want to go depends on how different your new domain is from the old domain. And so now, you have all these weights, you keep the weights fixed from where they were before, you take a new image, you propagate it through the network, you have a vector representation of each image, and now we're back to just training simple classifiers that everybody knows about. And so this idea of transfer learning is quite an old idea, but it was first used with deep learning with Jeff Donahue's paper with DCAP, and they used the AlexNet that I was just talking about to learn new features, or to train a classifier on the Caltech 101 dataset. Okay? So
what is the new dataset?
What's up?
What is the new dataset?
So the new dataset is Caltech 101, and we're going to try and recreate some of those results. Not fully, we don't have the time, but we'll get most of the way there. And I'll describe the dataset in a little bit more detail in a second. Okay. Okay, so no spoilers. I'm gonna clear everything. First, we import GraphLab. Then we load Caltech 101 into our S-frames. And then I'm going to get the classifier going as well, since that takes a little time. Okay, now I'm going to go back and talk about the Caltech 101 dataset. It's basically 101 natural images. It's a dataset that was collected maybe probably 10 years ago by a Stanford group, and they're smaller than ImageNet, but they're sort of similar in nature. The problem is, though, that there's very little data for the classes. Some classes might only have 30 images per class, and the decision boundary between the classes has to be quite complex, because you're still trying to discriminate between things that can be quite similar. So this is a pretty natural place for using our deep features. The domain is fairly similar to the ImageNet domain, and you have very little data. So we're just going to basically adapt the model. So let's see how our model is doing. Let's go back. Okay, so we learned the classifier. The logistic classifier is just logistic regression. It's an instance of those linear classifiers that I was talking about before. And so I get 99% training accuracy after 5 iterations, and this is only 30% of the training data. So we were getting probably on average 8 images of each class. So so there's a danger of overfitting there. Let's see how we actually did. Let's evaluate. And we get 77% accuracy. Now, the state of the art, as of a few years ago, was 85%, but it was doing these exact same steps. The only difference is there wasn't a subsampling step, and there wasn't so they used the full data set, and they also let the classifier run for a few more iterations. And my computer is going haywire. Sorry, guys.
Same.
was extremely little work for a result that maybe a few years ago would have seemed unattainable without a lot of handcrafted feature design. Okay.
Just move your window to the.
The problem is my trackpad is completely unresponsive right now. Okay. I'm sorry, guys.
Blame Tim Cook.
I'm gonna blame Apple. Command what? Command tab. Okay, yes, so I can tab around windows. That's nice. And now I have a responsive trackpad again. Kind of. This is great timing. I'm glad you guys are here to see this in my moment of glory. What's that? I might be able to restart the computer.
Just try closing your screen and opening it again.
Okay.
Yeah, that's the soft boot. It may be caused because of, it's very finicky when it comes to AirPlay.
That's true.
Yeah.
AirPlays cause a lot of problems.
Okay, so my windows continue to be unresponsive.
We
So
can all,
let's
we can all huddle around here.
So-
engineers to fix it back?
So I'll field a few more questions while we shut this off and turn it on again, maybe?
No, don't,
Okay.
don't do.
Okay, any questions?
Could you compare and contrast GraphLab to Caffe, Torch, Piano, and any other open source deep learning libraries?
So, sure. So,
Peter, repeat the question so that the rest of the audience.
yeah, the question was, how does GraphLab Create's library for deep learning compare to other open source options such as Caffe, Piano, and Torch? Okay, and I'll answer that. Magic? Almost, it's not showing up. Okay, I'll answer that this way. So Piano is quite low level. You're not defining network architectures, you're actually performing the matrix operations and defining the networks that way. Torch I'm not very familiar with, I'll be honest, and Caffe is very specific to deep learning. So while I'm giving a talk about deep learning here, GraphLab Create integrates this deep learning toolkit well with other machine learning toolkits, such as like nearest neighbors classifiers and nearest neighbors graph creators, and also other classification algorithms. So if you were to try to do this feature extraction thing with Caffe, for instance, you'd have to use Caffe to extract all the features and then dump them somewhere, load them in elsewhere, and perform your classification that way. So there's an ease of use thing there. But fundamentally, Caffe and GraphLab Create end up making very similar calls to CUDA APIs. So, all right, I guess I'll continue with the presentation. Okay, so now we have this new workflow of transfer learning with deep features, which I just showed to you guys. You have some labeled data. You extract features using a neural network. I did not show that because it takes some time, but with the ImageNet model, we can process about 200 images a second right now on a sort of an average GPU. And then, so once again, you split things into training set and validation set. Now, on top of these feature vectors, you can learn a simple model, you validate it, it probably works fairly well. And then you can deploy it in production and make money and be happy. Cool. So what else can we do with these deep features? So we have really semantically meaningful representations of any natural image now. And so, I mean, you should be able to use this for a variety of different things. And one natural thing is that finding similar images, right? So if you have like a vector that represents one image, what happens if you just search for the nearest neighbors of that vector? What do you find? And so I'm going to give you guys a fun demo where, using exactly these features, we retrieved similar shoes. Okay. Let's hope this works a little bit better than the last time. Shoes demo. Okay. So once again, we start off by importing GraphLab. We import the image. This is basically an S-frame of a shoe catalog. Okay, so we import this, we load in this S-frame. Now we can look at it. This is our visualization tool, GraphLab Canvas. But you can see that basically it's just a whole ton of different kinds of shoes. There's boots, there's sandals, flats, and anything in between. And so the next thing we do is, like we were talking about earlier, we load in this ImageNet model. So guys, bear in mind that this ImageNet model probably did not see any images of shoes. So this transfer learning is quite remarkable. So let's take a look at the pre-trained model. It's a neural net classifier, as we expected. It was trained on about 1.2 million images. At a top 5 accuracy is 85%, which was what the AlexNet basically reported. So now I'm going to go ahead and extract features from some image. This is some just random image in the S-frame. And this is what one of those features looks like. This is the thing that tells you this is the representation of an image. It's still not something you can just look at and is interpretable, but it's apparently just very semantically meaningful. It's 4,096 dimensions long, and that's because the second to last layer of the AlexNet has 4,096 hidden units. So one nice thing is that I'm going to print the length of the raw image and the extracted feature. So the raw image has about 200,000 pixels. So even though 4,096 is still quite a long feature, it's still a lot smaller than the input. And so that's part of what makes it more tractable for classifiers. Okay, so one key thing about neural nets is that they have a fixed input size. And so anytime I need to extract features from an image, I want to resize that image to the size that the original model was trained on. So in this case, this is commented out, but you want to resize to 256 by 256 by 3. Okay, so I'm going to build a nearest neighbors model. Okay, and so that was just a construction of the model that allows you to query an image with its nearest neighbors. So I'm going to take an example of heels. I'm basically just pulling out an image out of the S-frame that happens to be heels. And so let's take a look. It is, in fact, a heel. And now I query the nearest neighbors model with 10 nearest neighbors. So we're going to look at the 10 closest images to those heels. So we can see that the closest one is itself. It has a distance of 0. Then as you go down, you have larger and larger distances of 45. Whether that distance is meaningful in absolute terms, it's not really clear, but the relative distances are important. Okay, so now let's take a look at those nearest neighbors. And the original query image is in the top left, but you can see that all the nearest neighbors are strappy heel shoes. And I was almost surprised at this word myself, because shoes just aren't in ImageNet. But apparently the same thing that's useful for discriminating between like natural images and animals is also useful in discriminating between shoes. Okay, let's do one more example. This time I'm going to pull out a cowboy boot. And let's look at that cowboy boot. Did I do the show? There we go. There's it's kind of a reddish cowboy boot. Okay. Now we can show the nearest neighbors. I see, it's still querying. There we go. And so, as you can see, all of the resulting images are cowboy boots. So, one natural thing to ask is, what's least similar to a cowboy boot? So we show the last 10, the least similar images. And we get, honestly, things that aren't even shoes. So that's pretty good. So somewhere in the middle, something that's between being really close to a cowboy boot and not being a shoe at all. We can show that as well. And you get sort of low profile flat shoes. So how am I doing on time here?
10 minutes.
10 minutes? Okay. So, I mean, I find that really remarkable. Shoes or deep learning has made a really big impact on computer vision, but it also has made a big impact on text. So I'm going to switch gears a little bit, and I'm going to spend just a few minutes talking about how you can use similar ideas, although not identical, and apply them to text problems. Okay, so just very basic, the most basic classification you can do with text is just with a bag of words. So in your entire data set, you create a vocabulary, and for each input, you basically create a histogram or count of how often each word occurs. So on top of that, maybe you can use some kind of simple classifier to classify your text. You can also perform some kinds of transformations which weights some of these values relative to the total occurrence, so something like TF-IDF. But most recently, Mikolov and crew had designed an algorithm called Word2vec, which is a neural network for finding deep features for words. And basically how it works is like this. It's called the skip-gram model. And from a given word, in this case dog, you try to predict nearby words in a sentence. So let's have the sentence, a dog went for a walk. With the input dog, you're trying to give high probabilities for words A, went, for, A, and walk, and low probability for other words. Okay? So you use a neural net for this. And the internal representation, which I'll zoom in on in just a sec, can be viewed as deep features. Okay, so how does the neural network actually look? This is it. I'll go ahead and say that maybe it's a bit of a misnomer to call it deep learning, although that seems to have caught on. You only have one hidden layer and one output layer. And the input layer is of dimensionality of the entire vocabulary. And so for each input, you have a one-hot encoding of that word. So for instance, maybe the word dog is represented by index 2 here. So index 2 would have a value of 1, and everything else would have a value of 0. And from there, you would go through this neural net, and you would try to predict, give high probabilities for the nearby words. And just like before, if we wanted a deep representation, a deep feature, embedding for that input word, you would go to this hidden layer and just pull out the vector there. And so this is how related words sit next to each other in high dimensional space. Basically what was done is these high dimensional, 300 dimensional word representations were, the dimensionality was reduced to 2, I think via PCA. And you can see that there's interesting relationships. Like on the left, you have countries. On the right, you have capital cities. And there's even some kind of ordering semblance of, maybe cities that are more east are on the top, and European cities and cities that are more west are on the bottom. So this is kind of cool. But just, for a practical example, this is something that we trained on a blog corpus in one of our for one of our blog posts, actually. We found that the word lol, LOL, has nearest neighbors such as haha, yeah, ha ha ha, hee hee, laughing out loud. So it does actually work. And it's very cool that you can have these actual vector representations for words, because then you can do things like predict the gender of the author with high accuracy. And how you might do that is maybe an averaging of all the word vectors in a text snippet, or maybe some other scheme. Okay, so one last thing is how is this relevant to a data scientist, right? This is all very cool, but how can you use this? Well, basically, we just squeezed this entire pipeline into a very small bit of time, and it's a very small bit of work. So, I was showing you in the demo, the data cleaning and feature engineering was, you don't even really need to do feature engineering because of deep learning, and data doesn't have to be very clean, so all you have to do is load the data in. This data intelligence thing, well, you already have this pre-trained model that somebody has trained for you, so that's hardly any work at all. And so the last little bit that's left is deploying the model to production, and we happen to have something called predictive services, which basically just with a few short lines of code lets you host this model as whatever model as a service. So we've compressed this timeline considerably, and so you can use the power of deep learning very quickly and effectively. Okay. Using deep learning. So in real life, this is one example of one of our customers and what they managed to do with this pipeline. This is one of my favorite examples because it's just hilarious. It's a company called Oncology. They're trying to disrupt the trash business in San Francisco. And what they're trying to do is eliminate pickups. So they put cameras in dumpsters, and they just don't want trucks going to the dumpsters that aren't full. And so using deep features, we have managed to effectively have an accuracy of 96% for classifying almost empty and almost full dumpsters. And previously this was being done by mechanical turnkey, so it was not scalable for them. And this sort of stands out to me because, once again, these trash images are like very poor quality. They are definitely not related to anything in ImageNet, yet we just took that model and applied it and voila. So the take-home message is, these deep features are really remarkable. So, thank you. I just have a few final words. We have a data science summit and Dato conference on July 20th and 21st. So there'll be a lot of exciting talks and a lot of excitement going on there, so please attend if you wish. You can register at conf.dato.com. Another thing is that tomorrow at Galvanize in downtown San Francisco, we'll be holding office hours. So you can talk to me or Rajat then. We'll help bring your data, bring your laptops. We'll get you installed, we'll get you started. You can start having some fun with this stuff. And then the last thing is, give our software a try. Learn more at our Learn section of our website and at our blog. We are hiring, so keep that in mind if you want to move to beautiful Seattle. And go create something with Dato and have fun. Thank you.
Awesome, thank you. We'll take a few questions. If you let me come to you, you can speak in the mic.
So, thanks. Does deep learning give us an understanding and visibility into the features that it creates at each of those layers and levels? Like, how did it compute them, and what sort of transformations, feature engineering happen at each layer?
So the question is, do you have visibility into what the network actually learned at each of these